So hi, hope I am audible. Myself Subrata Samanta and I am your teaching assistant for the thermal physics course taken by Professor Dev Banerjee this semester at NPTEL. I am a first year PhD student in the Department of Physics at IIT Kanpur. So first share my screen. Screen. Yeah, so hope my screen is visible now. So in the previous class, we briefly discussed about various cyclic processes and concept of engines, etc. So today I will going to discuss about briefly about the thermodynamic potentials. So today I am going to discuss briefly about just a minute. Okay, so today I am going to discuss briefly about thermodynamic potential. So so far we learned that the functions of states. Okay, so what is the functions of state of a certain systems, that it does not depends on the path that we are working on. Okay, so it's only depend on the initial steps and the final steps. Okay, so irrespective of which route we take through the parameter space, like some parameter space means that the variables, the pressure, volume, temperature in this parameter space, so that does not depend on the routes, okay, or path. So they are only depend on the initial state and the final states. So the things that we learned so far, that is the internal energy. One of the example is the internal energy, right? So internal energy is a state functions, and other things that is like the entropy, right? But that we discussed in the previous class or and before that, so that the volume and pressure are also kind of functions of states. Okay, but the work done and the heat, they are not functions of states. So they are depends on path, but the functions of states, so the function of states, so this is the internal energy, let's say U, and we, yeah, so one is the internal energy, and second is that there's entropy. Entropy is, and some pressure, volume, T, right? So these are very useful quantities, and pressure, volume, temperatures, right? But these two are very useful quantities. Okay, so what I can do, we construct a new functions of state in the combinations of these functions of states, right? So any combinations of the functions of states, we construct a new functions of states, right? So and these functions of states are called the thermodynamic potentials. Okay. So like the example, let's say U plus Ts. So we combine these variables in such a way that the quantity must have the dimensions of energies, right? Otherwise we cannot add this. And U is a function, is a dimensions of energy, and Ts is also dimensions of energy, must have a dimensions of energy. Okay. So when we add two quantities, they must have the same dimensions. Okay. So one combination is that U plus Ts, right? So is a thermodynamic potential. So what the dimensions of the potentials are the dimensions of the energies, right? So the dimensions of the potential are the dimensions of the energies, right? So U plus Ts, and another is the, let's say, U minus PV, U plus 2 PV minus 3 Ts. Any combination, you can write that U plus 2 Ts. Okay, we can write that U minus, let's say, 2 PV. Okay, U plus let's say 3 Ts. So the sign is does not matter, right? So you can choose plus sign or minus signs, whatever, but it gives a quantity that is the dimensions of energy, and they are called the potentials. So these are called the thermodynamic potential. Thermodynamic potentials. But not all the potentials are useful, right? Very useful. So the specific form of these potentials are useful is called that U. So the useful, not all the thermodynamic potentials are useful. Not all these thermodynamic potential are useful. So not all these thermodynamic potentials are very useful, right? So some of these are useful, and this is a very specific form. Okay. So one is called that the enthalpy. So let's say internal energy. One is that internal energy. So internal energy is one kind of thermodynamic potentials. Internal energy, it's U. It is called the enthalpy. Enthalpy is H. So this is U plus PV, and 3 is called the Helmholtz free energy. Helmholtz free energy. So enthalpy Helmholtz. Let's set the Helmholtz free energy if this is U minus Ts. For is the Gibbs free energy. Gibbs free energy G H minus Ts. Okay, so that means if you write that U plus PP minus Ts. So these four are very useful. So, and they are all the combinations of this U and the other state variables. So all are these state variables, right? Functions of state. So they are only depend on the equilibrium states, the initial and final state. They are not depend on the paths. Okay, specific paths. So these four thermodynamic potentials are very useful. So why they are called the potentials? because so if we compare that so what is that if you know that the work done W, right? So this is PdV. So let's say dW is minus PdV, right? So this is your work done dW minus PdV. So we can write this as a, in general, that F time dx, right? So dx is the displacement and this is the force. So this is called the generalized displacement and F is the generalized force. So F is the, it's a generalized force and X is the generalized okay. So X is the generalized displacement and F is the generalized force, right? So now is this F, right? So this force F is the minus del V del X. From classical mechanics we know that this V is a potential, right? So this V is a potential and X is a displacement. So the derivative of the potential with respect to displacement gives a force, right? So now in the thermodynamic systems, so this is from classical mechanics. This is a classical mechanics. So recall your classical mechanics context. So classical mechanics. So F is equals to minus del V del X. Okay. Just a minute. Okay. So so now come back to the in the thermodynamic case. So in the thermodynamics, that if let's the in this case dW is minus PdV. So so P is the generalized force. Okay. So this P and dV is the generalized displacement. It's the volume, right? So we can write this P. How to write this P? So this P is write this, let's say minus del F del V at constant temperature. So that means this F, okay, so in this case we can write this F as a curly because otherwise 2F confused. So this is a curly F is a force, okay, and this is F is the Helmholtz free energy. So this F is the Helmholtz free energy, this is a force. So this is a force. Okay. So this F del V and del Vt. So V is, oh again there is a V is the potential. So again we can write this yeah, so we can write as a capital V. How to write? Yeah, so we can write so this V is a potential, okay? It's not the volume, okay? So this V is a potential, okay? We just writing down the different colors. So this V is a potential and this F is a force, okay, but this V is a volume. So here this V is a volume, right? So then we can see that del F del V, so this is a Helmholtz free energy with respect to the derivative of the Helmholtz free energy with respect to the volume gives a pressure. So this F is looks like a potential in your classical mechanics. So that's why it's called the thermodynamic potential. So that's why F is called that the thermodynamic potential. So any quantities with respect to the derivative with respect to something else and gives a force, so they call the potential. So that is the classical mechanics contents, and it applies everywhere. Okay. And that's why it's called that the Helmholtz energy is a thermodynamic potential, and similarly for other variables are also other variables that internal energy and enthalpy gives energy also thermodynamic potentials, because the derivative with respect to others it gives a generalized force. Yeah. So we'll see when we explicitly discuss these potentials. So let's first start with the internal energy. So we know that from first law of thermodynamics that du from the first law of thermodynamics we know. Let's first the go into the internal energy. Internal energy. So the internal energy is U. Okay. So from first law of thermodynamics, know that du equals to that dq plus dw. So this dq and dw are inexact differentials. Okay, so they are not functions of state, but du is a function of state, and it becomes an exact differentials. Okay. So for reversible process, we write that dq is tds from the second law of thermodynamics. Okay. So this S is entropy and T is the temperatures, and minus dw is PD, right? So it's a well known. Okay. So then we write TDS du plus PD, right? So that means U is a function of both S and V, right? So both S and V. So those variables are appear in the derivatives. Okay. So these are the argument of this variables, right? So that means that it implies that U is a function of S and V. It's the argument, two arguments S and V. Okay. So only the arguments that appear in the derivatives. Okay. And these are the extensives. Both S and V are the extensive variables. And this P and T are the, so these S and V are extensive, and so that's why they are appear in the derivatives, because U is a extensive variable, so U is a extensive, right? And this T and P, okay, so this T and P are the intensive, so they appear as a component. Okay, so these are the intensive variables. So that means U is a function of S and V, right? So suppose that S and V are constant of a systems. Suppose S and V are constant of a systems. Suppose S and V are constant. This implies that du becomes 0, right? So that means that the energy is the same, right? That means energy is also constant. Energy does not change. So now we can write so du, so, since that u is a function of s and p, so u is a function of s and p, so we can write that du of the partial equation. So we know that the del u del v at s dv plus del u del s v ds, and compare equations 1 and 2, we get that the the form of the temperatures and the pressure. The form of the temperature th del u del v del u del s v, and the pressure is minus del u del vs, right? Okay, so similarly for second, the enthalpy H, so this H is u plus pv, and the imperceptible derivatives of H dH is that du, right? You know that the du is tds minus pdv. Now pdv is that the pdv plus pdp, so pdv cancel, so tds plus pdv. So that means the age is a variables of s and p. Okay? So that means that age is a variable of s and p. Okay. So age is a variable of s and p. These are two arguments. So you can similarly write down this temperature and volume. Okay. So we can write this temperature T is del H del SP, and volume V is del H del PS. Okay. Okay. So similarly for Helmholtz free energy, for Helmholtz free energy, Helmholtz free energy, if there is u minus df, and we just derivative this df. So you know that the dA, the tds minus pdv, and the derivative ds is the tds minus sdt. So tds cancel, is minus pdv minus sdt, right? So that means that f is a function of t and p. Okay. This is of temperature and volume. Okay, so from this we can write that the s in terms of minus del f del dv, and p is written in terms of minus del f del dt. So in the similar way, you can write the 4 is the Gibbs free energy. So this G H minus ds, right? So you can write this dg H dh Okay, so this dH minus TdS minus STT. So now we know that the dH is put into this, the dH is TdS plus VdP, right? So we get minus STT plus VdP. So that means that G is a function of P and P, right? So the form of this potentials construct, so how to construct this form of the potentials? This actually constructed by the Legendre transformations, right? So the specific form of this potentials, okay? So you know that the U is a function of S and B, right? And you construct that the some quantity that is a functions of, or you construct some functions that that is contains S and P, right? So the exact form of the potentials construct by the Legendre transformations. So exact form of the potential constructed by Legendre transformations. Constructed by Legendre transformations. Okay. With proper signs. Okay. So things that suppose you construct that U is a function of S and V, you construct some functions F, okay, as a functions of, let's say, T and V, right? So this V is unchanged, okay, just to replace S and T, so this is just U minus TS, okay. Similarly, if we construct, let's say, from this we construct say G, T and P, right? So here that both are changes, right? So S and V variables are changes to T and P variables. So that's why we call that U minus TS plus PV. Yeah. The sign conventions is actually comes into that the P and V are collectively as a minus signs. Okay. So if you choose your sign conventions, this is that U minus TS plus PV. Okay. So in this way, construct the other potentials. In this way, you can construct the other potentials as well. So now, why we need this various kind of potentials, okay, and why these four potentials are specials, right? That means we want to try to work out how to find the equilibrium properties of a systems when it plays contact with the surroundings, right? So how to find the equilibrium properties of a systems, okay? So the question is that how to find the equilibrium properties of a system Okay, when it is placed in contact with its surrounding. When it is placed in contact with its surrounding, right? With its surrounding. So in general, a system able to exchange heat with its surrounding and also to work on its surrounding, right? So let us now consider a systems and in contact with surroundings. So let's consider a system so this is our system and these are things of the surrounding, right? These are things surrounding. Okay. And the surrounding kept at constant temperature T naught and constant pressure P naught, right? So what happens when we transfer energy du and the volume dv from the surrounding to the system, right? So the internal energy change in the surrounding. So we transfer energy du from the surrounding to the system. So what is the change in the internal energy of the surrounding? So this du naught equals to minus d, right? Because this du naught is the change in the internal energy in the surrounding, that is the negative sign, and this du is the change in the internal energy of the system, right? That's and if we take a system is positives, then the surrounding is negatives. Okay, so this du naught is a change in the internal energy of the surrounding. Change in the internal energy. Sorry, change internal energy of the internal energy of the surroundings. Okay, and this du, so notice du is that so this is the change in the internal energy of the system, and this du naught we can write in terms of t naught p naught. So t naught t s naught minus p naught, again that dv is the change in the volume, so surrounding volume changes is dv is minus, right? So du and dv are the system changes, and when we apply from the surrounding changes, it becomes a minus. The surrounding changes are denoted by that p naught, t naught, okay, s naught, and du dv are the changes for the system. Okay, so when we written down in terms of the surrounding changes, we become a minus sign. Okay, Okay, so then we can write this change in entropy in the surrounding. Okay, so we can write explicitly that the negative sign so negative sign express the fact that the energy and volume in the surrounding are decreases. Express the fact that the energy and volume in the surrounding are the surrounding are decreasing. Okay, so then we can write this ds naught, the entropy, in terms of du, so minus du plus p naught dv divided by t naught, right? So the total changes, so this is the amount that changes the entropy in the, so this is the amount that changes in the surroundings, right? So the total change in entropy, that is the system plus surrounding. So this is the ds total change in entropy. Okay. So change in the total change in entropy means that the delta s or ds 0, the change in the surrounding plus ds change in the entropy. Okay. And from the second law of thermodynamics, still does the total change of entropy is greater than equals to 0, right? From second law of thermodynamics. So now put into this type of formula, put into this, that in term the written in term ds in terms of this du and dv. So we get that t naught times ds total equals to minus du plus p naught dv, and ds is minus t naught ds minus t naught ds. So this quantity must be greater than 0. So hence this du plus p naught dv minus t naught ds is less than 0. Right? So this quantity must be less than 0. Okay. So now we define the ability A u plus p naught v minus t naught s. So this p naught t naught are constants, and this U, V, and S all are the system properties, and P naught, T naught are the surrounding properties. Okay, so define the ability A, and yeah, and the system, if in equilibrium, if the system, if in equilibrium, the system is in equilibrium, is in equilibrium, that means that dA, okay, so that means that dA du and P naught is constant, so P naught dV, again T naught is constant, T naught ds is must be less than equals to 0 from the above conditions, from these conditions, from these conditions. So this dA must be less than equals to 0. So this dA must be less than equals to 0. So that is the conditions for the systems to is in equilibrium. Okay. So it's a general conditions. It depends on U, V, and S. Okay. So suppose if yeah, so suppose if your systems let's say it's yeah, constant volume and constant entropy, right? S and V, and then we can minimize the energy, okay, and go to the equilibrium states, right? But not the always. Okay, suppose you change the suppose the system is depends on the another variables, right? And then the energy is not to minimize to get the equilibrium state, right? So we have to minimize something else, and that's why we define the various potentials, and so we need the potentials depends on the system parameters. Okay, so which kind of potentials we need, and that depends on the system parameters. So but this the ability, so we define this ability, so ability is always less than equals to 0, right? So this is the general conditions to uh, for systems to in equilibriums. Okay. Okay, so let's do some examples that let's say system with fixed entropy and volume, fixed entropy, right, S and volume V. So consider systems where the entropy and the volume are fixed, right? So then ds equals to 0, dv also 0. So now the ability dA is du. So only left du. Okay. So look into this equations that dv and ds 0, then only left the du. So this must be less than equals to 0. So that means in these systems, you're minimizing the energy. Okay, minimize U to find the equilibrium state. Minimize U to find the equilibrium state. Let's see, this is a case 1. So now we are going to case 2. This is a system with fixed entropy and pressure, not volume. So that's a system with fixed entropy S and pressure P. So that means that ds equals to 0 and dp equals to 0, right? So then if we write this dA, so this du plus p naught dv and ds equals to 0. So this p naught, this pressure constant, so this pressure constant, let's say this p equals to p naught, a constant, okay, and which implies that dv 0, so that's why written in p naught. So du plus p naught dv, this must be less than equals to 0. So now from the thermodynamic potential we define that the enthalpy H is U plus Pv, right? So if pressure is a constant, then we can write dH, so H is U plus Pv. Now pressure is a constant, so U plus P naught V. So you can write dH is du plus P naught dV, right? So this implies that dH must be less than equals to 0. Okay. So minimize H to find the equilibrium state of the system, okay, where the entropy and the pressure are fixed. So minimize H to find the equilibrium state of the system, okay. So similarly for other case, let's say system is thermally isolated. System thermally isolated, right? So that means no heat can enter to the system, okay, and the system cannot do cannot do work on its surroundings, right? So thermally isolated means that dq is 0 and dw also 0. It is isolated systems, okay. So that means that the system cannot do work on its surrounding, or the system can do no work on its surroundings, okay, because system is thermally isolated. So in this case, that du equals to 0. The first of thermodynamics, du equals to dq plus dw. So if the system is thermally isolated, then this du becomes 0. So then we can put into this formula, that's dA equals to du plus p naught dv minus d naught ds. So we get that dA equals to only minus d naught ds. So du 0 and the thermally isolated, so the volume is also constant, so dV 0, right? So d here is only the minus T naught ds, so that is less than 0, right? So this implies that ds is greater than 0. So that means when the system is thermally isolated, okay, so entropy is maximized, right, to find the equilibrium state. So maximize entropy to find the equilibrium state. So maximize entropy is to find a equilibrium state. Okay. So that means it's not always true that we have to minimize something to get a equilibrium state, right? So here is the example that we have to maximize entropy to find the equilibrium states for a thermally isolated systems. So one more, let's say case 4. What is the meaning of A? Yeah, A is that we define a quantity that is called the availability. So it we define a quantity that is called the availability because so we are not using anything rather than the total change of entropy is greater than equals to 0, right? So we write down the system properties and the derivatives of this in terms of other variables, and we apply this ds total is greater than equals to 0. So we end up with these conditions. Yes, so this is a surroundings and this is a system. So these are the systems and this ds naught. Okay, so anything denoted by this naught with these are the surrounding properties. Okay, and the system properties are without knots. Okay, so the ds total from the second law of thermodynamics that tells that the ds total must be greater than equals to 0. So from second law of thermodynamics, now we put into this ds naught in terms of other variables du and dv from these equations. So we end up with these inequalities, right? We end up with this inequality, right? So now we define this quantity as a availability because this is a true in general, right? So this is true in general. So now we define the availability A in this way such that the du it becomes this, right? So once we derivative this dA, we end up this. Okay, so that means if we define this availability and we write down that this quantity, this u naught minus p naught v minus plus p naught v minus t naught s, so this is your availability. Now we once we derivative this dA and we write this du plus p naught because p naught is constant, p naught dv minus t naught ds, and this inequality tells that this must be less than equals to 0, right? So that means in short that dA must be less than equals to 0, right? And that is the ability. So if we write the ability or if you just work with this long inequality, so as your choice. Yes, but P naught is constant, right? So it's a surrounding yeah, so the system pressure and temperature changes, but surrounding pressure and temperature is not changes. Yeah, like a reservoir. Surrounding pressure like atmosphere, okay, atmosphere pressure and temperature. So we are assume they are kept at fixed. So these are the surroundings, right? So now we are dealing with the systems. So now we are considering there's a systems. Okay, so system with fixed entropy pressure, system with fixed entropy and volume, right? But these are the surrounding. Surrounding are kept as a constants. Yes, yes. Entropy change in the surroundings. Yeah, so the S naught is extensive variable. So energy, entropy, they can change because uh, we put so why this is a change in the internal energy of the surroundings, right? And because the things that so we consider that when we transfer energy and entropy from the surrounding to the systems, okay, then we can write these equations. So how to write this energy change in terms of the other variables. So when we write down the energy, the change in energy, so we can written in terms of ds naught and dv, right? Because energy is an extensive variable, so we can write down in terms of the how much entropy changes and how much volume changes, right? It's clear or not? Yeah. Yes. That's why this is a negative sign. So if we so means that the energy transfer from the let's say surrounding to the system, right? That means the surrounding energy decreasing, system energy increasing. Yeah, system internal energy increasing, right? And surrounding internal energy decreasing. And that's a negative sign. If we put that the du is negative, that du in even not is positive. So this is a negative sign express that the fact that the energy and the volume in the surrounding are decreasing, right? Yes. And so if we define this ability in terms of things, so this inequality is just come from the second law of thermodynamics. And this is true in general. So whatever your systems, so we apply, check that this ability is less than zero, right? So in order to do that, the some quantity is greater than zero. Let's say this case. So when we apply this the system in thermally isolate, then du equals to 0 and this dA is minus T naught ds, so this must be less than equals to 0, so which implies that this ds is greater than equals to 0, right? So that means that the entropy is maximized in this case, right? Yeah, so dA is right without not, so we are only dealing with the systems, right? So every we're not talking about in this case the surroundings. So surroundings are fixed at something, but we are only dealing with the systems. And so when we're going to the equilibrium state, so which quantities minimize or maximize, that I have to find out. Yes, in order to get a equilibrium states, right? So similarly, suppose system with a constant volume and constant temperature. So with system with constant let's say volume and temperatures, constant volume and temperature T and volume P, right? Then you write this dV equals to 0 and dt equals to 0, right? So but in this case we see that the dA is only depends on the dV, right? It does not depends on the dt, right? So we can this dA, then we can write the dA is du minus t naught ds, right? Because dV is 0 and the temperature is constant, that's why we write this t as a t naught, right? As a surrounding temperatures, right? So system temperature is constant and we take this system temperature T as a T naught, as a surrounding temperature. Okay, yeah, system is obviously connected to that. So when they are thermally isolated, then we say that there is a no things that, yeah. So we can write this T naught or any T whatever, but we are just only focusing that ds is greater than 0. Okay, but in this case that temperature is, let's say, constant, and we are say that the temperature is constant, that means they are in surrounding temperature T naught, right? So then we can write this dA is du minus T naught ds. This is less than equals to 0, right? So now we are so then so this, what is this quantity? So then recall that the Helmholtz energy F is U minus Ts, right? So now your system is fixed at temperature T naught. So that means U minus T naught S. Then we can write dF equals to du minus T naught ds. So that means in this case we have to minimize Helmholtz energy. Right. So we have to minimize F to find a equilibrium state. Yeah, so minimize F. So one more is left, that is the Gibbs energy. So let's say there's a system with constant pressure and temperature, constant pressure and temperature. So then dP equals to 0, dt equals to 0, right? So I denoted that P as a surrounding pressure, T as a surrounding temperature, right? So system temperature is equal to the surrounding temperature and system pressure is equal to the surrounding pressure, right? So then we can write this dA du minus P naught ds minus P naught dV. So this must be less than equals to 0. So now recall the Gibbs energy G is U plus P naught V minus T naught S. So we just write P as a P naught and T as a T naught, right? Because the constant pressure and temperatures. So then we can write down the differentials dg, it's du plus P naught dV minus T naught ds. So that means in this case that dg must be less than equals to 0. So for this system, to minimize G to find a equilibrium state, to find a equilibrium states. So this G is a Gibbs energy, right? So that's why the so we are discussing the various situations, okay, for constant entropy, volume, and entropy, pressure, and volume, temperature, pressure, temperature. So the four potentials, okay, this form of this potential u minus ts and u minus ts minus pv. So these four potentials are appears, okay, have to minimize these things, okay. So that's why these only four potentials are important, okay. Other combinations you have to construct a potentials, but that are not very useful in the thermodynamics, right? So that's why the only four form of these potentials are important, but you can construct in many out of this, okay. So you can construct that u plus 3ts, u minus 2pb, or any other combinations, okay. So the dimensions of energy, you can construct a potentials, okay, combinations of these variables u, v and pts, so you can construct a potentials. But the only these four potentials are very useful in the thermodynamics, okay? Because when we considering different systems, okay, so we have to find a equilibrium states, so we have to minimize one of these potentials, okay. Okay, so now we are discuss Maxwell relations. So it's a relations that is useful to solve the thermodynamics problem easily. So the Maxwell relations is basically Maxwell's relations. So Maxwell relations is basically that suppose it's a state functions if, right? So if must be functions of states. So and this if a functions of states and they depends on these variables x and y, right? So you can write this del f del x y dx from the partial differential equations and del f del y x dy, right? So now know that this f is a functions of state, functions of state. That means this df must be exact differentials. So this df must be exact differentials. So the conditions of this exact differential is that, so you can derivative this del x del f del y at constant x, right? So del f del y, so this must be equal to del y of these other variables del f del x. They must be same if df is a exact differentials, okay. So in general is that df, let's say this m dx plus n dy, right? So if df is exact differentials, then delta m delta y is delta n delta x. So that is the conditions. So then so I have to work out one examples. So let's say the Gibbs free energy, the examples on exercise that dg, the Gibbs free energy is minus sdt plus vdp, right? So then we can write this dg, but in general g as a functions of t and p, right? So we can write this dg del g del t at constant pressure dt plus del g del p at constant temperature dp. Then we compare, okay? So that means if is minus del g del t at constant pressure and p del g del p at constant temperature, right? So now we apply the same thing, that if dg is a function of state, sorry, g is a function of state, right, is a state function, then dg is a exact differentials. So then this del t del g del p, right, is equals to del p del g del t, right? And you know that the del g del t is a s, so this implies that del v del t equals to minus del s del p, right? So this is one of the Maxwell equations. So this is one of the Maxwell equations. Yeah, so we have to write the what are the constants. Okay, so in this case del g del p at constant temperature, and in this case constant pressure, right? So constant del p del t at constant pressure, right? And this is a constant temperature. Yeah, just a minute. Del g del p t. Yeah. So you have to write the constants. Okay. So in this way we construct the other Maxwell relations. Okay. So it's basically that the Maxwell relations is basically another way we can say that so if is a internal energy state functions, okay, therefore it does not change in any cyclic process, right? So that means that the area, so when we calculate, let's say pdv in the pdv diagrams, okay, and we consider a cyclic process. So let's say this is a pdv diagram and we go into the ts diagram, right? So the cyclic process goes to the another cyclic process, okay, but the area remains the same, okay, because the internal energy is a state function, so it does not change in a cycle. So the area remains the same, that means the close this pdv, it remains the same, it's ts, okay. So in which planes you are calculating, that is does not matter, the area remains the same, right? So hence we have that then yes, internal energy 0, yeah, cyclic change, yeah. And this no change means that a reversible process, yeah, it's a reversible process, then it's no change. If it's a irreversible process, then this due to this cyclic process, even if the cyclic process, there is a finite change. Gives free energy is only functions of T and P. Yeah. Okay, number. Okay, so the thing is so we know that what are the thermodynamic variables, right? So the thermodynamic variables P, V, T, S, U, right? So now we construct. Let's say that so far we know that only the potential is the internal energy, right? So now internal energy is a functions of S and V, right? So now we construct a potential that is a functions of pressure and temperature, right? And that is called the Gibbs energy. So by definition, we construct this is a functions of temperature and pressure. Because when we're dealing with a system that is constant temperature and constant pressure, right? So we need a potential to deal with this, to find a equilibrium states, okay, this kind of thing. So and that's by definition we call that this is a Gibbs energy. Okay, and this is actually useful for the phase transitions things. So how to so we constructed this in that so exact form of this potential constructed via the Legendre transformation. So we call that U is a SV is a functions of SV. Now we construct G as a functions of T and P, right? So by Legendre transformations we have to do how to do that U minus Ts plus Vp, because it changes that S to T and V to P. So that's why. So when we changes U to as a USB to FTV, right? So V is a constant same, but we changes S to 2. So by Legendre transformations tells that U minus T is the exact form. So in this way we can construct. So what are the variables we need, and appropriately we change define the potentials. Okay. So the area remains the same, and that means then how this one of the integral connected to the other integrals. So because this is so we can write this as a double integrals dp right, and then we can put a Jacobi, right, Jacobian, because when we go one coordinate system to another coordinate system we need a proper Jacobians, right, and that is DTDS, right. So this is the area enclosed. Okay, so you know how to write the area dx dy, so in this case dp dv, okay, and in the ds plane the dt ds. So this Jacobi must be 1, okay, in order to get this two equals. Okay. So this implies that delta ts and delta pv, which must be 1. So then we can write this delta ts by delta xy equals to delta pv by delta xy, where xy is any other thermodynamic variables, right? So we can take in that xy as a tp, tv, ps and sv, right? We construct the four Maxwell equations, right? So we choose this xy, these four combinations, we construct. So construct four Maxwell equations. Okay. So in this case that so area must be the same. area must be the same. Okay, so how to know that the area must be the same? Because in the PV planes, okay, what is this area enclosed by this curve, it gives the no work done, right? So it's the work done, right? And is the heat in the TS plane, right? So now we saw that in the cyclic process, the internal energy is a state functions du equals to 0. So that means the amount of work done is equals to the amount of heat. So it will be 0, and that's why they are equals. Okay. So du is a dw plus dq. Okay. So du equals to 0. That means dw equals to dq. That's why the area must be the same. Okay. Okay. So now, okay. So now going to the heat capacity. So you know that for ideal gas, for ideal gas, the heat capacity. So heat capacity, the definition is that the C, the dq over dt. Right? This is the heat capacity. So for gaseous systems, we have to define two types of heat capacity: Cp, this del q over del t at constant volume, and Cp del q over del t at constant. Du by dt is yes, but yeah, this is a general definition. So you can write this dq as in terms of du because the volume which does not change for a closed systems. Okay, yeah, only terms of du. This is the general definition. So for ideal gas, so this is for the gaseous systems. So for, and this is the in general. So this is the definition of the heat capacity for in general, and this is for the gaseous system. For gaseous system. So for ideal gas, you find that Cv is 3R by 2, right? Just easy to calculate. So if you say that the U is the energy is from the equivalence theorem, you know that the 3 by 2 RT in mole gas, so RT, and we can write this Cv du dt. So it's 3 by 2, right? 3 by 2. So that means the Cv is a constant, but this is not the case. Okay, always. So the Cp is also depends on the volume and pressure. So how do I know that? So in general, the Cp is del q del t at constant volume. Now we know that the dq is a TdS, so T del S del t at constant volume, right? So now if we say that the del Cv over del V at constant temperature, so that means del V. Okay, so now we like to calculate this. Okay, the variations of this. So this is in general. So the variations of the specific heat with respect to volume. So del V and T del S del T P. So it becomes that T, because T is does not depends on the volume. And T and V are independent, so we can take it outside. T del V del and del S del T P, right? So now we interchange because A is a state variable, so we can interchange that this T del T del H del V, right, at constant temperature, and outside volume. Right. So this del H del V T, now use the Maxwell equations. Okay, so I think I have write down this. Yeah, so del H del V T is it gives that T del T, and it's del P del T V. So that means this T del 2P delta T2 at constant volume. So this is in general how the specific heat changes with volumes. Okay, at Cp, so the delta Cp over delta V at constant temperature is related to that. So for ideal gas, just cross check that. For ideal gas, if you know that the P is in RT for in mole gas, in RT by V. So del P del T is NR by V, right? Del 2P del T2 is 0. So that's why the delta Cp del V is 0. So that means Cv does not depend on the volume. As we see that Cv is a constant. Right? But for more complicated real gases, okay, so this, the specific heat is not constant. They vary with volume as well as pressure. Okay. So similarly, if you constant the delta Cp over delta P at constant temperatures. Okay. So we find that this becomes that minus T del 2V delta T2 at constant pressure. Okay. So the Cp is not always constant. They also depends on the variable volume and pressure. But they both are 0. So these are 0 for ideal gas. For ideal gas, Cv and Cp are constants. Okay. So now, how much time we left? Yeah, 30 minutes. So now we are going to discuss the susceptibility. So what is that? There is a generalized susceptibility. Generalized susceptibility. So the susceptibility quantifies that how much a particular variable changes when a generalized force is applied. So we talk about that what is the generalized force. The generalized force, that suppose we write down that the work done dW is F times dx, right? So this dx is the generalized displacement and F is the generalized force. So for, let's say, for the gaseous systems, we know that this is minus P dV, right? For gaseous system, okay, so for gaseous systems, this dW is minus P dV, but in general this is a force, generalized force times generalized displacement. For gaseous system, the generalized force is pressure and the displacement is the volume, generalized. So the susceptibility quantifies that. So the susceptibility quantifies. And this is the generalized force. Susceptibility quantifies how much a particular variable changes, how much a particular variable changes when a generalized force is applied, so when a generalized force is applied, right? So again, the generalized force is that the pressure and temperature. So the force is the derivative of the potentials. Okay. So recall your classical mechanics constant that any force we can write down is a derivative of the potential. That's why it's called the potential, thermodynamic potentials. Because once we derivative with respect to this potentials, with respect to some other variables, we get a force, generalized forces. Yes, because exact differentials. All other state functions things are the exact differentials, right? So the force must be conservatives. Yeah. So an example that the generalized susceptibility is, let's say, del v del dx. So let's consider that the susceptibility is that the particular variable changes when a generalized force is applied, right? So generalized force is that T P, right? These are the generalized force. Generalized force. Right? So we write down that P as in terms of how to write P terms of, yeah, minus del F del Vt, right? So this is generalized force, right? Minus del F is a potential, and del V is a X types generalized displacement del Vt, right? And similarly, T is also generalized force. We can write down in terms of the other potentials. Okay. Just check that how to write the temperatures. Yeah, so we can write the temperatures till each. Yeah, so we can write the temperature T till delta is at constant volume. Yeah, so now the susceptibility. So in the general form of the susceptibility is that the quantify how much a particular variable changes when generalized force is applied. So let's say the susceptibility is that let's say del V del T. So generalized force T is applied, how the volume changes, some particular constant X. So keeping F constant, how much does the volume changes when we change the temperatures? So this is called the thermal expansivity. This is called the thermal expansivity at constant X. At constant X. So the thermal expansivity beta at constant X, that means we call that the beta X. Now we call the isobaric expansivity beta P. So isobaric expansivity beta P is 1 over V del V del T at constant pressure, and adiabatic expansivity beta S 1 over V del V del T S, right? So another useful the generalized susceptibility is that the isothermal compressibility Kt, okay, this is minus 1 over V del V del P at constant. So the minus sign is actually that when we increase the pressure, the volume must be decreased, okay? Because Kt is always positive, so and isothermal, and then adiabatic compressibility Ks is minus 1 over V del V del P. Yes. Okay. So this is that the volume changes with temperatures and volume changes with pressure, because only T and P are the generalized forces. Okay. And by definition is that has to quantify that the how much a particular variable changes when generalized force is applied. So these two things we have to define, that the expansivity and the compressibility. So volume changes with temperature and volume changes with pressure. And these are the expansivity and compressibility must be positives. Okay. So in this case, the negative sign implies that del P is negative, and this negative gives a positives. Okay. So then we can calculate this Cp minus Cv. So yeah, so you know that the entropy is a function of temperature and volume. Okay, so then we can write this ds del S del T at dt del S del V at constant temperature dV, right? Now with respect to its temperature at constant P, the derivative with respect to the differentiating this with respect to pressure at constant T, differentiating with respect to T at constant pressure P. So this del S del T at constant pressure is del S del T at constant volume times del T, sorry, plus del S del Vt del V del T at constant pressure. So now use the relations, thermodynamic relations, that del S del Vt and del V del Tp equals to some minus times del T del Pv. So we get this del S del V T del P del Tp. So these are Maxwell equations. Maxwell equations use Okay, so use these Maxwell equations. So how can write this del P del Tp? So you can write this del P del Tp in terms of other two variables minus del P del V T into del P del Tp. Okay. So then we get this Cp minus Cv so Cp minus Cv. So Cp, what is the definition of the Cp? Is T del S del Tp, right? Because dq is just, so we write down this here, right? Yeah. So this is just Cp T del S del Tp. So this is Cp T del S del Tp minus Cp T del S del Tp. So V. So now we put this formula that del S del T. Yeah. So you know that the del S del Tp and del S del Tp, right? So once you put this formula, so T del S del Tp, yeah, this is del S del T del V del T. So now we can put into this del V del Tp in terms of del S del V. Yeah, so you know the del V del Tp, and we replace this del S del Tt. 1 minute, del S del Vt. So del S del Vt, so T times del V del Tp, and del S del Vt, we know this is minus del P del Vt del V del Tp, right? So this is nothing but that we differentiate that. Yeah, so T times 1 over V del V del Tp times 1 over V del V del Tp divided by del V del V T 1 over V, right? Del P del V is 1 over del V del, and 1 over V, 1 over V, 1 over V. So we can multiply with a V, right? And we give a minus sign. This minus sign turn down here. So this is just nothing but that Pt beta p square by Kt. So that is the general relations that Cp minus Cv, it depends on the volume, temperature, and beta p square and Kt. So these are the experimental measurable quantities. Okay. So why we define this compressibility, expansibility? So these are the experimental measurable quantities. So once we measure this thing, we calculate this thing, and we know that the Cp minus Cv must be the same. So theoretically calculate Cp and Cv and subtract that Cp minus Cv, and you, the right hand side is measured experimentally, so you just measure it. Okay. Similarly, if you how to know the gamma, right? So the gamma, the adiabatic index. So there's a very, so once you calculate that the kt over ks, right? So that means the isothermal compressibility and the adiabatic compressibility. So this just 1 over v del p over t by 1 over v del p over s, right? This is by definitions. So now just put the thermodynamic relations, that this del v del P, so this 1 over v cancel, and del v del P is just related to the minus del v del t p del t del p v, and this is minus del v del s p into del s del p v. So and use the Maxwell relations. So this del v del t p and del t del p v. So del v del t p times del p del t p is minus del s del p p, sorry, minus del s del p, yeah, minus del s del p p by minus del p del s p times, we can use the Maxwell equations. So del v del s means that the del t del p v over a minus sign times del s del p v. So now we see that the minus sign is cancelled. So del v del t p del s del v p. So the same constant, right? So you can write this del s del t p by del s del p v. So now we multiply with a t, right? So that means so multiply with a t. So this is becomes that cp over cv, right? So this is a gamma. So this gamma is just kt by ks. So again, measure kt by and ks experimentally and divide it, so you get a gamma. That's the adiabatic index. And you know for different gases what is the values of gamma. Okay. Okay. So now we are to two more problems and then we stop. So one question is, let's consider a n mole monatomic ideal gas. So let's consider n mole monatomic ideal gas. Okay. So the equation is that PV is in RT. The specific heat per mole, specific heat per mole, CV is 3r by 2 for ideal gas, monatomic ideal gas, right? So 3r by 2. So to find it, Helmholtz free energy as a function of percentage, find its yeah. So find it Helmholtz free energy if as a function of in P and T. Okay. So how to okay. So it's easy to calculate that for an ideal gas. So we consider an ideal gas. So solution is that for an ideal gas. So for an ideal gas, this du, we know that the n CVDT. So this Cv is the specific heat per mole, right? And if there is a n mole, so that's a n Cv and times dt. Right? So in the thermodynamics, you always talk about the differentials. So we are never talking about the exact things. So exact calculations not happens in thermodynamics. Okay. So in the statistical mechanics, we calculate the exact energy or exact Helmholtz free energy, this kind of things. But in the thermodynamics, we always talk about the differences. So one equilibrium state and another equilibrium state, how much they differ, okay, and how they related to the other variables, okay, differences. So this du in terms of dt, we cannot write that u as a function of t. We cannot write that u as a in CVT, this kind of relations. Okay. So this is not valid in the thermodynamics. So you're always talking about the differentials. Okay. Yeah, we're always measuring the change. So one equilibrium system to another equilibrium, on equilibrium state to another equilibrium state, you always measure that how much the change in the particular quantity when the other quantities are changes. Okay, that is the thermodynamics. Okay, but in we don't know the exact value. Yeah, so that's why we so once you calculate the exact value, we go into the microscopic picture. Okay, yeah, so then we go to the statistical mechanics. But in the context of thermodynamics, the macroscopic properties, okay, the system we always talking about the differentials. So that means that we can write this u in CBT plus u naught. So this u naught is important. So on you, if you not write the u naught, then this is invalid. Okay, so the u naught is important. That some reference we have to write. Okay. So this is the internal energy of the system when the temperature T equals to T naught. So this is the internal energy of the system. Internal energy the system when the system temperatures when temperature T equals to T naught. Some reference temperature T naught. So you call the reservoir temperatures or something like that. And the system that U is in CVT plus U naught. Similarly, you can write that ds this ds. So you know that the du is tds minus pdv. So you can write down ds is 1 over t, and you know d in cvdt plus p by t dv, right? So this is, so put into this in cv. So what is the values of cv for ideal gas? This is given. So 3 by 2, so 3 inner by 2 So S is ln T, right, plus nr ln V. We use the equations of state ln V plus some constant is not prime. So now so entropy of the system is S naught when, so put that the entropy of the system, so this is specified, the entropy of the system is S naught when T equals to T naught and P equals to P naught. Okay, so here we written this the S naught prime, but with right now when the temperature, when the system entropy is S naught, when the temperature T naught and P naught, so we put in that into the above equations, we get that 3 nr by 2 ln T over T naught plus nr ln V over V naught. Then we write this is S naught. So S naught prime become S naught. So when we written this T equals to T naught and P equals to V naught, and after the one calculations you get this, right? So then the Helmholtz energy F is U minus Ts, right? So then you know that the U, right, is in CVT. So this is 3 nr by 2 T minus 3 nr by 2T ln T over T naught plus nr ln V over V naught plus F naught, plus F naught. So this is important, plus F naught. So this F naught is, where F naught is U naught minus T naught S naught. Okay. So F naught is U naught minus T naught S naught. Because the T is T naught, the temperature and pressure is P naught, the entropy is S naught. Okay. Okay, so now the another is that so consider the equations of states of a matter. Consider the equations of a state of a matter is, let's say, P is alpha times T cube over V. This dependency. And the internal energy of the matter and the internal energy of the matter is U, is a function of temperature and volume. Let's say B T to the power n, let's say A T to the power n ln P over V naught plus some functions of temperature. So find A and N. Yeah. So how to find? So how to start? So first of all, we look into the variables, right? So here is the internal energy is given. So this is a functions of T and V, right? what are the other quantities that depends on this T and P? So this is a very crucial point where we start. Okay, which potentials have to start from that. Okay. So let's say the entropy. Let's look into the entropy. That entropy. Yeah. So entropy depends on T and P, right? So that means write down that ds is du plus pdv by d. Right. So once you write this and you know that the du, so we can write this du as a del u del v d dv plus del u del dv dt, right? So you can write this, so 1 over t del u del vt plus this p times dv plus del u del dv 1 over t times dt, right? Sorry, this is a p over t. So now we put into the u and p. So we know this the p and we know the u. Put into this, so we get that ds is b t to the power n minus 1 plus, so a t to the power n minus 1 plus alpha t square over v dv and divided by a prime t by t plus n a t to the power n minus 2 ln v over v naught times dt, right? So now this df is exact differentials. Okay, so you can apply the same thing that the ds is an exact differentials. So this is, let's say, m and this is, let's say, n. Okay, so that means del n del v equals to del m del d. Okay, so which gives it gives that 2 alpha t minus a to the power n minus 2, it's become 0. So that means like that n equals to 2, sorry, n equals to 3 and alpha equals to 2a equals to 2 alpha. So how to start, this is the very important. Okay, so which quantity have to start? So then first check that the what is the variable. So and based on that we start with that. So entropy, enthalpy, or Helmholtz energy or Gibbs energy. So it depends on the variables. So what are the variables we are looking for? Based on that we can start and we can calculate easily the this kind of problems, solve. Okay, so the assignment problems are almost done. So, okay, so most of the problems we discuss here already. Okay, so let me stop here. We'll see in the next series. Thank you.